We have an exciting session. Okay, so we're starting the next session. Our next speaker is Eran Socher from Electrical Engineering. He's going to talk about metamaterials, right? All right.
Yes. Okay. Good morning, everyone. My name is Eran. I'm going to talk to you today about perhaps the more physical and engineering side of metamaterials that we're integrating inside RF and millimeter wave integrated circuits. Metamaterial, by its name, for those of you who are not familiar, it's materials that are not natural. It's going beyond the natural materials. And this is, and people do that because, beside the fact that it's interesting, people do that because the natural materials do not give them what they want. They want something extra, something beyond what the natural materials give us. And we see that phenomena also in integrated circuits, where the available materials do not necessarily give us what we want in terms of the applications and the performance that we need. It was suggested. I'm going to say just a few words about the lab. My lab is the high frequency integration lab, and we focus on design and characterization of integrated circuits at very high frequencies, up to 300 gigahertz. The lab was founded 4 or 5 years ago. The main focus of the lab is standard digital technology for integrated circuits, and we push this technology into the millimeter waves. Millimeter waves means 30 to 300 gigahertz of frequency. And the main applications that are driving this research are imaging, high-resolution imaging in radio frequencies, and high-speed communication applications, going beyond tens of gigabits per second. So we have some unique design and characterization capabilities at the lab. We do on-chip characterization of integrated circuits. And the group currently has 5 PhD students and 4 full-time master students, and some more master students working part-time also in industry. Okay, so what am I going to talk about today? First of all, I'm going to do some introduction to the world of CMOS, integrated circuits, and its opportunities and challenges in the millimeter wave frequencies. Then I'm going to talk about different kinds of metamaterials that we're integrating inside those circuits that are mainly based on transmission lines. So I'm going to say a few words about transmission lines, and then how we play with those transmission lines by changing effective permittivity, changing effective permeability, synthesizing right-handed transmission lines. And I'm going to show this by using examples of actual circuits that are doing some function based on these kinds of metamaterials. And then I'm going to say a few words about what we want to go beyond into the 2D metamaterials and conclude. So first of all, why do we talk about RF and millimeter wave integrated circuits, and in CMOS, in silicon? So the reason why we talk about this is because CMOS is undergoing a tremendous scaling trend in recent years, which means that devices are shrinking, going into the nano region already a long time ago. So right now current technologies are more or less 28 nanometer, something like that. And as a result of this shrinking, also the available frequencies that we can still gain on are steadily increasing, right now at a few hundred gigahertz. So it means that potentially we can have some useful frequency. This might become useful because we want to have very high resolution imaging, we want to achieve very high data rates in communication, wired communication. These need the high speed. So even though CMOS is mainly for digital circuits, we can do a lot of interesting other stuff with this integrated circuit technology. And just a couple of examples, because we have faster transistors, we can have amplifiers at high frequencies, as you can see here on the left. This is an amplifier at about 80 gigahertz, a frequency source, VCO, voltage-controlled oscillator at about 70 gigahertz. And if we have faster transistors, we can have circuits operating at higher frequencies. So what are the challenges? If you have faster transistors, supposedly all your problems are solved, and you don't need to do anything new. But in addition to the fact that we have faster transistors, if we want to justify the use of very high frequencies, millimeter wave frequencies, we need to cover a very large bandwidth, tens of gigahertz of bandwidth, to make this worthwhile. And what turns out to be reality is that making this happen really depends on the passive devices that we use, not just the active devices, the transistors that give us gain, but also the passive devices that really have an impact on the bandwidth, the actual bandwidth that we can have in our circuits. So what kind of passive devices do we have? So one of the oldest passive devices that people have been using are transmission lines. What are transmission lines? It's passive devices that direct and enable propagation of electromagnetic waves, mainly in a 1D fashion. We want to direct the wave in a certain direction along the transmission line. And if we look at the cross-section of the transmission line, it usually looks something like this. We have a signal line, we have a ground line. This is a cross-section. And there are certain variations. We can have a microstrip line, a coplano waveguide, where we have the signal here in the middle and also ground lines on both sides. And there are many variations on this concept. The main idea is to have the electrical and magnetic field here in the cross-section, quasi-TEM mode propagating along the transmission line. And these transmission lines are very useful. Creates resonance structure or impedance matching or all these kinds of ideas. And how do we look at these transmission lines? One way of looking at these transmission lines and analyzing them is actually noticing that it's a distributed structure where we have distributed along the transmission line, we have mainly inductance, series inductance of the wire, and parallel capacitance, the capacitance between the signal line and the ground line. And in addition, we have some loss. We have resistive loss here, R and G, that represent the loss that we have in this structure. And if we solve this distributed structure, we see that it supports propagation of electromagnetic waves that have very certain characteristics. It has, we have a voltage wave, we have a current wave. The ratio between their amplitude is the characteristic impedance, Z0, that is connected to the ratio of this inductance per unit length compared with the capacitance per unit length that we have. And this is related to the ratio of the permeability to the permittivity of the material that we have here in this structure, the effective epsilon and mu that we have here around the transmission line cross-section. And of course some geometry, a component that depends on exactly how we do it. And in addition, we have the propagation constant, gamma, that is also related to these properties. And we can also translate this into a phase velocity. And this phase velocity is 1 over square root of LC. Also related this time to the product of mu and epsilon. Again, material properties and some geometry factor, in this case, B. Okay? And of course, in free space, this phase velocity is the speed of light. And here we have mu naught and epsilon naught of free space. And this is, of course, the speed of light. Of course, when we have an actual material, it's going to be low. Okay, so we have transmission lines. It's very useful, and they depend on material properties. So what is wrong with that? The problem is that sometimes we're stuck with materials that do not give us what we actually want in terms of impedance, in terms of phase velocity. So we want to change those properties. Moreover, the transmission line that we get when we work at a certain frequency can be very large because it's in the order of magnitude of the wavelength. So if we have a wavelength of millimeters, it means that transmission lines are going to be millimeter long, and that's too much. We want very small chips. We want very small integrated circuits. And the properties are fixed. If we have a certain dielectric, this is what we have. If we have some magnetic material, this is what we have. And this results in relatively narrow band operation, because then you have a certain length of transmission line, you have a certain resonance at a certain frequency, and it's not wide enough. So we want to be able to control the properties. So we want to control the properties to tune them into what we want, and we want to control them on the fly so that at one time we have this property, and then we want to change, we want to tune into another frequency, we want to change the material properties. So we need some way of doing that. So how can we modify the properties of transmission lines in CMOS? Which actually means creating controllable metamaterials, because the material that transmission line is going to see is going to be something other than the natural material. And can we use that to create reconfigurable circuits that we can change their properties? So one way of doing this is controlling the permittivity, and this concept is called artificial dielectric, and it's actually a very old concept, dating back to 1948. And the basic idea is that if we take a material and we create some kind of metallic object, when we have an incident E field, we create a polarization vector, which in turn makes the effective dielectric constant different. So this is the basic concept. It was used initially to reduce the size of antennas back in those years. But we can adapt this idea into the integrated circuit world. This is a transmission line, a differential transmission line. We have a differential signal line here, propagating the wave in this direction. And our metallic objects that we introduce here are those floating strips here below the transmission line. And the effect of those floating strips is an increase in the effective dielectric constant that we see. This is no longer a homogeneous material, because this is not, the material does not behave the same in this direction and in this direction. And it's not homogeneous, but we get an effective increase in the dielectric constant, assuming we have a homogeneous material. So we can see the difference between two states where we have the floating strips here under the transmission line, and it's continuous, and when it's open, when we break a gap here between the two floating strips. Here we have no boost effect of the dielectric constant, and here we do have the boost effect. And we can see it also in measured results. This is the transmission line, floating strips here. Two experiments, open and short, we see the difference in the phase velocity. How can we control it? Remember, this is part of an integrated circuit. We have transistors. If we have transistors, we can use them as switches, and we can switch here between the two floating strips, between two states, open and short. Okay? So you can see here how this affects the phase velocity, and we can move from open state to short state. Of course, switches are not ideal, so we don't get as much change as in the ideal case, but we do have a change. And if we have a lot of switches along the transmission line, we have a switch here, and each of them is controlled individually, we can actually get steps in the dielectric constant that we have, or the phase velocity that we have in the transmission line. So we control it in a digital way. So we can take it even a step further, and this is a slightly more advanced structure, where we have also shielding here below to shield some of the effects of the silicon substrate below. And this is the floating strips that we switch using the transistors. And we use this transmission line in a distributed circuit that uses transmission line. What kind of circuit can use transmission line? One example is a distributed amplifier, where we have a transmission line here in the input, transmission line here in the output, and some gain mechanism between them. But we want to go a bit beyond this amplifier. So if we take the output of the amplifier and feed it back into the input of the amplifier, we can get an oscillator because the signal repeats itself. So this is what we see here. So we can have like a differential transmission line, distributed gain stages along the way, and we take the output and drive it back into the input. So we have what is called a traveling wave oscillator. The wave travels along the transmission line in some kind of a loop. We have gain on the way, like we have in a laser, to compensate for the losses, and we have oscillation. So one example of how to do it is like this. We have a transmission line section, and we have several gain stages along the way to compensate for the losses. And this is a traveling wave oscillator that produces 8 phases, because on the way here we have 0 and 180 degrees, here 45, 225, so on and so on and so on. So we can actually have oscillation here with 8 phases. And I remind you that each of these transmission lines is controllable, digitally controllable. We can change the phase velocity of the transmission line. If we change the phase velocity of the transmission line, we change the oscillation frequency, because the total length that we have here for the transmission line sets the oscillation frequency according to Barkhausen condition. The phase, the 0 phase that we have here, after going the whole way, needs to be 0 again. So this depends on the effective length. Also, an effect of generating several phases is if we use rectification, we can multiply frequency. So we can use those phases to generate second harmonic, fourth harmonic very easily. So we do that as well. So we take this structure, we kind of squeeze it so that it would be more area efficient, like this. And this is the implementation in 180 nanometer CMOS technology. And so this is the traveling wave oscillator, and here we drive the fundamental, second harmonic, fourth harmonic out of the 8 phases that we have, and this is digitally controlled. So we can see here the digital control. This is the actual frequencies, and this is the digital control. We have like something like 30 steps of frequencies that we can control by changing the phase velocity of the transmission line. So what about magnetic properties? We can change the dielectric constant. Can we change the magnetic properties of the transmission line? And this is CMOS. We don't have anything magnetic in CMOS. Okay? So how can we do that? So again, this is the differential transmission line. So if we want to change the permeability, we can integrate loops here along the transmission line. And this is similar to the concept of split ring resonators, if people were familiar with this concept. But here, because this is part of an integrated circuit process, and this is CMOS process, we can switch those rings. So when the ring is open, it has some effect. It actually has some boost effect on mu. And if we switch the switch on and we short these, we have a decrease in the effective mu. Okay? And we can see the concept here like this. Basically, we have the distributed inductance along the transmission line, and we couple the ring inductors to this distributed inductance, and we switch this inductance. So basically, we have here a transformer, and by switching here, we change the effective inductance that we have here along the line. So if we short it, we decrease the inductance, and if we open it, because of the parasitic capacitance that we have here, we actually have a boost. So we can play with that, and this is a transmission line. I'm not sure if you can actually see the rings here inside. Here there are 3 rings, and it's switched. Okay? So we can see a digital change in the phase when we switch one switch. This is an example of 6 switches. 6 loops, we can change the phase velocity here along the line. And we can use that to implement an oscillator. How does that happen? We can take this transmission line, use it as a resonator. We change the effective length of this resonator by changing the magnetic properties. So we can tune the frequency. So this is how it looks. This is the resonator. This is the transmission line. Here we have the loops with the switches along the way, in this case 5 loops. And this is the whole oscillator with the output buffer. And this is used at millimeter wave frequencies. So we're able to tune between 55 and 69 gigahertz of oscillation frequency, which is kind of a record in this range, because it's very hard to tune frequencies at high frequency. And we can do this digitally. So you can see here all the states and how the frequencies change, and we can compensate for nonlinearities. And this is also this is also a very big advantage of this method. Okay, so we can change the electric constant, we can change the magnetic properties of the transmission line, and there is also the problem of size. We said the size of the transmission line can be very large. So one way of mitigating this is synthesizing transmission lines based on lumped elements instead of the actual length of the transmission line itself. If we use lumped elements, we can use a lumped inductor instead of the distributed inductance along the line, and this is much more area effective. We can squeeze in the inductance in a much smaller area, also for capacitance. So we can do that. So, for example, we can use this in a distributed amplifier that I mentioned before, but instead of using a real transmission line based on some natural material, we can synthesize this transmission line by using a lumped inductor, and the capacitance provided parasitically by the transistors that we use, and the transistors that we distribute along the line. So this provides amplification. We have an input line here that drives a signal to the distributed transistors along the way. We have an output transmission line here, picking up the signals from all the transistors, combining them in phase, so we can get amplification. This is very useful using those transmission lines because it's a transmission line, so it's impedance matched in a very wide frequency range. But if we synthesize the transmission lines, and it's not natural transmission lines, we can have the transmission lines either right-handed, like this, series inductance, parallel capacitance, like in nature, okay, like in the regular transmission lines that we use, but these are lumped elements. Or we can have a high-pass structure or a left-handed material where we have series capacitor and parallel inductor. Interestingly, the characteristic impedance looks pretty similar. It's, again, this square root of the ratio of L and C of the elements that we're using, but the difference is in the cutoff frequency. Is it a low-pass structure where we have an operation up to a frequency of a cutoff determined by the size of the lumped elements, or we have a low cutoff frequency and it operates at high frequencies, like we see here in this structure? And we can actually use this. So we can have a low-pass structure and have a distributed amplifier that has low-pass characteristics, and this is an example of such an amplifier. And this is how it's implemented. Okay, so you can see here the inductors along the way. Okay, the capacitors we don't see. The transistors are somewhere here in the middle, very small, and they contribute the capacitance that we have. And we can get amplification in a very wide frequency range of tens of gigahertz. And we can use this also in high-pass or left-handed structures. So here we have the transistors, and the transmission line that we have, remember, it's series capacitance and then shunt inductance. Series capacitance, shunt inductance, both at the input and at the output. Here, to boost the gain, we actually have a distributed amplifier here, high-pass, driving another stage of an amplification, driving a third stage of amplification to get more gain. And this is aimed at higher frequencies. This is a high-pass structure. And this is how it looks in actual realization. Again, most of what we see is the inductors. And this is the performance. I said it's high-pass, but in actual results, it's always band-pass, because at some high frequency, your gain is going to drop. You're always band-limited. So we have this kind of bandpass operation, and this is able of amplifying frequencies in the range of 50 to 70 gigahertz, which is also very wide band, and also very useful around the 60 gigahertz band, where there are some major commercial applications. Okay, so we saw that we can amplify low pass, we can amplify high pass by synthesizing those transmission lines. But if we do something, some kind of combination, let's say the input transmission line is low pass, the output transmission line is high pass, so we can have one frequency at the input, maybe another frequency at the output. So we can create a frequency multiplier. Okay, and this is what we see here. So we have an input which is low pass for low frequencies, relatively low. We have the actual active devices, transistors. We can use them as amplifiers, but we can also use the nonlinear performance or effects that we have in those transistors to generate, in this case, a third harmonic. And then the output transmission line is high pass. So it transmits the high frequencies, and it does not transmit the fundamental that we want to reject. So this is how the circuit looks. This is the input. Relatively low frequencies, I mean, compared to what we're usually doing, something like 10 to 40 gigahertz. And the output is 3 times that frequency in this structure. So we can have very nice results at the output, somewhere between 40 gigahertz and 80 gigahertz, with very nice output power that this frequency tripler gives us. And the fact that we have 2 different transmission lines at the input and the output are manifested in the return loss that we have, or the impedance matching that we have at the input and the output, that are targeted towards different areas of frequency. Okay, so this was all one-dimensional, and nowadays we're thinking how to make these things also two-dimensional. Okay, so if we take the same concept, we have, let's say, a series inductance, shunt capacitance. One-dimensionally, this is transmission line. But if we synthesize and we have a two-dimensional array of such inductors and capacitors, we can have a two-dimensional metamaterial. Okay? And again, we want to control. We want to control the effective inductance that we have. We want to control the effective capacitance that we have. If we change those properties, we change the material properties, the effective material properties. So we can actually control propagation in different directions. So this is part of what we're trying to do. And again, this is part of an integrated circuit, and we've seen that we can change those properties. So this is just a recent example. We just got the chip back. We didn't measure it yet. So this is a 2D array. Okay, we see again all the inductors here in a 2D mesh, and we have also capacitors here at the nodes. And what we want to do with this chip is we want to control the propagation in this 2D array by changing the properties that we have here for these individual cells. In this example, to control, we have an input coming here on the left side, and we want to control either to transmit a wave here to the output here on the right, or to actually reflect this kind of wave here by using the 2D array to the output that we have here at the bottom. And this is just an example of what we can do with this kind of 2D control of the wave propagation. But again, we haven't measured this chip yet. So to summarize, we have seen that we can suggest metamaterials based in integrated circuits where the motivation is to improve the frequency bandwidth of RF and millimeter wave integrated circuit. We have seen that we can change a dielectric constant and implemented this in an H-phase VCO. We showed that we can change the magnetic properties, implemented this in a V-band. V is 50 to 75 gigahertz. V-band VCO, another oscillator. We synthesized right-hand and left-handed transmission lines to create distributed wideband amplifiers and also a frequency tripler. And I've shown you some initial concepts of how we want to take these ideas into the 2D metamaterial world. So I want to thank you and acknowledge the contribution of graduate students, engineers working with our group, and the support of Ministry of Defense, Science, Intel, Agilent, RAD, and Broadcom. So thank you for your attention.
Can you say something about millimeter wave imaging applications?
Okay, so millimeter wave is interesting for imaging applications because it has the benefit of RF that it can go through different types of materials like clothes and things like that. But on the other hand, the wavelength is low enough to make a meaningful picture. So if you want to image a person, then you would get reasonable resolution. Not like optical resolution, we're not there yet. But if you want to take a... The what? RF yes. So by shortening the wavelength, you can get better and better resolution, and this makes sense. Also for radar imaging, three-dimensional imaging, if you have more bandwidth, then you can get better range resolution. So you can create also better resolution in the range direction. So this is also very, very important. So this is one of the major driving applications for millimeter waves. It's used and people are starting to use this for concealed weapon detection, let's say in airports and stuff like that, because those waves are reflected by metals and absorbed in the body. So you see the contrast. So this is very useful. Yes.
In a series of harmonic generation, how high can you go in frequency?
You can go as high as you like. I mean, you can generate, and there are also some commercial equipments that are based on, 18th harmonic, 32nd harmonic. The problem is the efficiency. So once you go to higher and higher harmonics, their conversion efficiency gets smaller and smaller and smaller. So the problem is not generating the frequency, it's generating enough power. So one of the things that we are looking at when we want to generate very high frequencies, let's say in the terahertz range, where you don't have amplification from the transistor itself, so you want to base yourself on harmonic generation, is how to do it effectively. And this is one of the hot research topics right now. What is the right trade-off between what kind of harmonic you use and what is the fundamental frequency that you use. And this is a very interesting trade-off, because it's still a big challenge to generate high power in the terahertz region. So the whole concept of harmonic generation and exactly what harmonic to use, what frequencies to use, what devices to use, how to do the topology of power combining, phase rectification, stuff like that. It's very interesting, and this is part of what we do.
Okay, thank you so much. We learned a lot.
Thank you.